today is more primary decompositions, yet more, except actually this is the main day. This is when we actually really do most of the stuff. So what have we done so far? We defined all the stuff, played around with it. We did primary decompositions of monomial ideals and the Alexander dual, which is really important stuff. And now we're ready to do sort of the general situation. So yet more PDs. And then also, I think next week, it depends how we do this week. I want to do integral closures, but I also want to get your ideas of anything you'd like to see in the last couple weeks of class. The very last day of class, we'll probably do presentations. But anyway, so here's the situation. So the first thing is zero-dimensional ideals. Okay, now I am going to be presenting some stuff here. Some of the stuff, a lot of the stuff that I've done is in some form or another in the file I handed you. So so you can decide whether it's worth taking notes or not for that. But okay, so I, as usual, is going to be sitting inside of a ring K of x1 to xn, which we'll call R. There's a standing notation for actually a large part of the course. Okay, and the situation here is so we're interested in the case when I basically defines a finite set of points. Okay, so let's be a little more careful about that. So our situation here is K is equal to a field. For the moment, it can be any field. We're going to have to make some extensions. And suppose that we have a K is contained in L as an extension field. E.g., the algebraic closure. Okay, so now the reason I do this is that in the Jupyter notebook, K bar looks pretty awful. So I'm sort of trying to use L instead. So it's not exactly a great mathematical reason for using this L. But anyway, so but this is but it could be any extension field, and we have I here. And then we have defined, well, I don't know if we have actually defined it exactly. The zeros over L of the ideal I is the set of A1 to AN. Okay, we're in n variables, A1 to A1, in L to the n, such that F of A1 to AN, when we plug it in, we get 0 for every F in I. Okay, so this is the usual thing. I'm just being a little bit more careful with what field it is that we're talking about. So as a simple example, we have I is equal to, this is a really simple example, x squared minus 5, y squared minus 1, sitting inside of, say, Q of joint xy. And the zero sets of I, oh, not of sub I, sub C, say, of I, or of R, actually, is what? This is about the simplest zero-dimensional ideal that you will see today. So this is going to be the set of points plus or minus root 5 plus or minus 1 contained in C to the 4, C to the 2. And it's 4 points. The number of elements of this thing is 4. By the way, if you look at this, if this is R here, R mod I as the curl, this is always very confusing. This is the curl dimension, right? So this is equal to 0. You all buy that? You have to make sure you recall with this. We have several ways of saying what it is. You could look at what primes are larger than I. Well, this gives you a bunch of actually a couple different primes, but they're all zero-dimensional. They're all finite. They're all maximal ideals, so it's going to be dimension 0. This is the same thing as, and what's the dimension over the base field, in this case Q of R mod I, is what? So we have this thing here. This is 4-dimensional over the base field, and the basis of it would be all the monomials not in the lead term ideal. So that would be 1, x, y, and x times y, or their images. in R mod I. Okay, so I write it that way, but you really think of it as the images as elements inside of here. Okay, so you can always write down a basis over this in some way like this. So anyway, this is the example, and this 4 is the number of points. This is really what is going on most of the time. Not completely all the time, though. So we'll have to deal with that. Okay. So here are some questions. So let's do it over here. Okay, some questions. Okay, so we're given I such that R mod I has dimension 0. Full dimension 0, i.e. I is 0 dimension. Okay. Those are synonymous to each other. And the question is, 1, how do we tell if it's finite? Oh, actually, I guess I didn't want to shoot. Well, that's okay. We'll leave that out. Actually, how to tell if I has dimension 0? Okay, if this is the case, R mod I. Okay, so is it easy? If I give you an ideal I, can you tell right away? And the answer is yeah, pretty much, as long as you can compute a Gribner basis. And the second thing is, how about computing the radical of I? In this case, the radical of I is I. There are no other polynomials that multiply up to that. That needs checking. But at any rate, we want to be able to compute this. Indeed, we want to then compute a primary decomposition of I. And minimal primes, associated primes, etc. Okay. So these are all fairly closely related, but let's get to that in a bit. So the first proposition is the following are equivalent. So if I is some ideal contained in K of x1 to xn, which is as usual R, the following are equivalent. Do I have enough room here for it? I think I do. 1, this dimension over K of R mod I is less than infinity, okay, over K. And this is equivalent to dimension of R mod I equaling 0. You should check and make sure you believe that. Okay. The second condition is the geometric condition. And this is that the number of elements in the 0 set over the algebraic closure of K of I is finite. Okay. And the third condition is the most interesting condition. Well, actually, those are good. This is the algebraic notion, is that you have a vector space. That's actually really useful to have a vector space that's finite dimensional, and that's equivalent to having at least the number of points being finite. And the third thing is, let's let this be a monomial order. On R, on the monomials of R. Then the lead term ideal of I, so we just take a look at all the generators of the Gribner basis and look at their lead monomials. This contains a power of each variable. So x1 to the a1, I guess I'm using here, up to xn to the an. Okay. For ai greater than or equal to, well, I guess if this is the unit ideal, then maybe I should say, actually, if it's a unit ideal, I'm not sure if that counts. It's 0 dimensional. Yes.
In your example.
Yeah.
Why? I mean, plus and minus 1 are.
That's right. R mod I is the vector space generated by all the monomials over R and their images mod I, right? So think of X, you can call them X bar and Y bar if you want, but for R, that's an infinite dimensional thing. That's all monomials. But whenever you have an X squared, you can rewrite it as 5.
But if you have a field and you extend by an element that's already in the field, you don't get in the field.
If you have an wait, sorry, say that again.
You have a field, and you say, and you pick an element that's in the field, you say, extend the field by this element. You get the field.
So the question is, if you have a field and you have an element and you extend it by an element in the field, then you have the same field.
Yes.
Yeah, that's right.
So isn't plus or minus 1 around? I'm a little confused. Like my intuition about it.
So the first of all is that the zero set here really needs to be considering everything. For instance, if I take x squared plus y squared equals -1 over the reals, I get empty set, and that is really not enough to tell me anything geometrically about it. So I really need to be working over the algebraic closure. So I need to look at all the zeros of it over the algebraic closure, and that's what that is. Over Q, there are no solutions. It is empty. Okay, not because I mean, so the y coordinates are rational. That doesn't help. It's still an empty set. So it wouldn't be particularly useful. It wouldn't tell you anything about the degree, the dimension of this thing. It wouldn't tell you anything about the geometry of it, because it might not even be zero dimensional in that case. Because even though it's empty, even if it's a finite set of points over the reals, it won't necessarily be empty. I won't necessarily be zero dimensional. So zero dimensional is actually quite a strong condition in this setting. So it's not the same as saying, so for instance, here, in order to extend the field to get all these points, I have to add in the square root of 5, right? But that doesn't change the dimension. That just changes the base field that I'm working over. So in both cases, I'm going to have a 4-dimensional, for any field containing Q, this will be a 4-dimensional vector space.
But y squared minus 1 is not a vector space.
No, that's why we get plus or minus 1 there. Yeah.
I'm just not following, because plus or minus 1 is rational. So I don't see how it makes the bigger. I don't see why the dimension of the Q is R mod I is 4. You can see it being, well.
No, but even it wouldn't even be 2 here. I mean, if you were looking at it as the number of points or something like that, there are no points because of the square root of 5s. So just because one of them happens to be rational, it doesn't. So remember though that the dimension of this thing is really related to the number of points, not what field you're over. Okay, if the dimension over Q is 4, but the dimension over the complexes is also 4, dimension over any field in this case, even if I did a finite field, that would be 4-dimensional. So so it's just not related to the number of solutions in Q, or even whether the elements are in Q, because
well, what if instead of y squared minus 1 is y minus 1?
then it would be the dimension of the field would be 2 over it. And I mean, the dimension of R mod I would be 2 over that, over Q. Because it would be x squared and y. And so the only monomials outside of that would be 1, x,
Yeah.
and that's it. Okay.
All right.
Okay.
I think I see. No, you're not just looking at the base field.
No, it is looking at polynomials and trying to figure out where they're 0. And it's complicated because this is not a field or anything. This is, in fact, that's the whole point of the primary decomposition, is to figure out what that is. Any other questions? Yeah.
Should we be letting the AI be equal to 0 if they're from?
No, I don't think so. Let's suppose that if I is not equal to R. Okay.
Like if it was equal, then we would get some 0 over here.
If one of these is 0, then this is the unit ideal. And if that's a unit ideal, well, the dimension of this is less than infinity, it's 0. So and that's also an empty set. So it's less than infinity. So it is a true statement, but I really want to not dwell on that. So let's just make I not equal to R. because we're never doing the primary decomposition of the unit ideal. It just, I mean, the primary decomposition of the empty list of components. Yep.
In question one, how to tell if R mod I has dimension 0, is that control dimension?
Yes, has Kroll dimension 0. And this is how you tell that. Now, this proof is so first of all, 1 and 2 is sort of the basics of the first class in algebraic geometry, and I'm not going to go back over that. Just if you don't know it, just buy the fact that these things are the same. Although a book that is pretty good is Becker. I've mentioned this before. It's pretty good in some ways. Fennig on Grosvenor bases. Okay, so it's a book in Springer, and it's on Grosvenor bases, and in chapter 8 it does primary decomposition. Maybe it's chapter 8 and 9. I kind of forget what the chapters are. It's sort of a couple different chapters. And what's nice about it is it goes through and does this kind of stuff. It proves the equivalence of these things. So if you are having any issue with that, that's a great place to. I think that the proofs are a little overly pedantic, but on the other hand, they're there. So that's actually quite nice. So, okay. So anyway, let's do sort of the idea of the proof. Well, the main idea is actually if it contains these things, then showing that this is finite is there's only a finite number of monomials that are not in here. And so that so therefore so 3 implies 1 is maybe I shouldn't say idea of proof. This is really most of the thing, but so 3 implies 1 is that all monomials or the images, all images of monomials x1 to the k1, say, xn to the kn, where ki is between 0 and strictly less than ai. These generate R mod I over k. Maybe I should be using boldface k's, but at any rate, we'll not worry about it too much. I'll try not to use k as an index. I am using k1 to k as an index, but that's not k. Okay, so in any case, it's probably a bad idea. But anyway, so this is how you get that that's finitely generated. How about 1 implies 3? If this is now a very cool thing that's going to happen here. Okay, suppose that we have that this is finite. So suppose the dimension over k of R mod I is equal to d is finite. Okay. It's probably pretty easy to immediately show that there has to be something in there, but here's a really good way to do it. So consider, I actually teach this for minimal polynomials in my linear algebra class, right? So you consider 1 xi. This is given I, 1 to n, say. We take xi, we take xi squared, and we keep going. If I go up to the dth power, I have d plus 1 elements in this vector space. So consider these in R mod I. So I'm really thinking of 1 plus I, xi plus I, but I don't write that. Okay. So I have d plus 1 elements in a d-dimensional vector space. Therefore, there exists a linear dependence, C0 plus C1 xi plus ... plus CD xi to the d is equal to 0 in R mod I. And therefore, f sub I, which is equal to C0 plus C1 xi plus ... plus CD xi to the d, this is 0. That makes this as a polynomial in I. Okay, as a polynomial. So these are actually elements in R mod I But when it's equal to 0 in R mod I, it just means that that's in I. So, and therefore, xi to the, so there, one of these is non-zero. Some ci is not equal to 0 since it's a linear dependence. So therefore, xi to some power ai is in the lead term of I for some ai.
Using two different ways. We want to say CJ is non-zero.
Yes, I want to say Cj is not equal to 0, and then xi to the ai, I don't know, ai is just one of these powers. Okay, is 0. So you're right. I want to say some Cj is not equal to 0. So
that's in the initial
xi, not necessarily, because all these might be non-zero. So then you have to take the, you'll take this one. So what I'm saying is that there is some polynomial in there, just in there. So the lead term of it, whatever it is there. And note also that ai is less than or equal to d. Okay, we don't need that for the proof here, but that's what we get. Does this make sense? Anything about my my words that make it confusing? I can imagine that being the case. Because this, I have a, by the time I get up to degree d, I have a linear dependence. That means there is some polynomial of this form. It might be that the CD and CD minus 1 are 0, but some of these are non-zero. So I look at the largest one that's non-zero, and that's the power AI. Okay. So this is actually a really good thing, because dealing with this as a vector space, you can use all sorts of nice vector space techniques to prove things about this ideal. And this is the first one. So already, so as a corollary, so I'm going to leave that. That's the end of the proof of this thing that I want to do. That really does prove 3 and 1 are equivalent. Okay, so corollary. Do I have a corollary in here? Is that corollary? The dimension of R mod I is 0. That's the Kroll dimension. I will be pretty careful about putting the sub k if I'm thinking vector space dimension. Okay, so this is equal to 0 if and only if for every I between 1 and n, there exists an univariate polynomial in xi in k of xi and in I. Okay, so that's kind of a cool little fact. It's actually kind of fun when you actually start playing with these things. We'll be able to compute those, and then you can really get your hand exactly on what's going on with these things. It's just nice. Here's a couple facts that we're not going to prove, although the first one is how many points are there if I take over the algebraic closure of I and I look at the number of points inside of here. What do I get? This is actually less than or equal to d, which is the dimension of R mod I over k, or k bar. It doesn't really matter. It's going to be the same dimension. So this d, which is the dimension, is actually very closely related to this, but it's not identical, which makes sort of sense. However, if I is equal to the radical of I, so it's a radical ideal, and k is perfect. We'll talk a little bit more about perfectness later, but and k is perfect, then in fact, the number of points over k bar of I is precisely this number d. Okay, this is actually the thing that is proved in Beckman by Stunning. So that's getting the equivalence, but a more precise equivalence over here, where that's equal to d if and only that's equal to d. But it needs two things. It needs that it's radical. That makes sense, right? Because if I have if I have an ideal that is not radical, it's going to have multiple, like for instance, e.g. Here are two examples that are of interest. How about I is equal to x to the fourth contained in k of x. This has dimension 4 when you quotient by it, but there's only 1 point, no matter what the field is. So then one holds and 2 fails. That's one good example of it. That's if I is not radical. But if I is radical, what could possibly go wrong? Have you ever seen any of these examples? Suppose Suppose K is the finite field on P elements, could be on Q elements, I don't really care, but P elements, but it's a fraction field over this. This is the field that whenever you think of a K is not perfect, this should be your go-to thing that you have in your mind. Okay, because this actually appears in real life, and so whenever you see, oh, I can assume K is perfect, no, you can't always assume K is perfect. So you have to sometimes be careful about that. Okay, but anyway, how about this one? And now what if I is equal to oh well, we might as well do it in one. How about x to the p minus t? Okay, contained in k adjoin x. This is a radical ideal. There is no you cannot factor this polynomial. But how many points are there over the algebraic closure? The algebraic closure has a pth root of this. So this polynomial becomes x minus t to the pth root, quantity to the p, and it's not radical, and this fails. So then also the number of points of v k bar over I is how many? It's x is equal to the root of pth root of t, and that's equal to 1, which is not equal to p, which is the dimension of the quotient. If this is R. Okay. So later on we'll be seeing, this is always a good example to keep in mind. It's actually quite a good example. It really if you can prove something without addressing this somehow, then your proof is wrong. And so you have to sort of think about that all the time. Okay, you can move this over to here perhaps. Okay, good. Okay, now let's talk. Okay, so this is just basics. Okay, zero-dimensional ideals are easy to determine. You calculate a Grosvenor basis. You just look to see if there are polynomials that have pure powers of the variables in it. And if it does, awesome. It's zero-dimensional, and otherwise it's not. We still don't know anything about primary decomposition or everything. So here's the properties of a primary decomposition for I of dimension 0. Okay. So suppose I is equal to Q1 intersect ... intersect QR, and QI is PI primary. What can I say? So these PIs, some of them will be possibly in the usual case, right? Is that we have a bunch of minimal primes, we have a bunch of embedded primes, and that's what we've got. Okay. So what is it? What happens here? So pose this, and I is dimension 0. Okay. Well, if you think about it, the minimal primes here have to be, it's really quite funny, actually. They're maximal ideals. So the minimal primes are maximal ideals. So, but note, one is each piece of I must be a maximal ideal. If it's not, that means there's another prime larger than it, in which case the dimension of I, it has a chain of 2, so it's dimension 1 at least. So that can't possibly happen. So each pi must be a maximal ideal. Well, that means that no two of them can be, that means no two of them can have a containment relation. And therefore, all the p sub i's, p1 to pr, are minimal primes. Okay. So that means, we already knew that which primes there were is independent of what the primary decomposition is. But now what we can do is we can take elements from each one of these things, an element that's in the intersection of all of them but one. Okay, so so this one is that Q sub I is uniquely determined. I think we already showed this, but let's just do it again, so that I'm not sure if I just said it or we actually did it. But here, what does this mean? What I want to do is I want to choose oops, I got my notation messed up. Fi to be in the intersection overall j not equal to I of Qj. Okay. But I don't want it to be in Qi. Now, can I do that? Well, yes, because if this were equal to Qi, sorry, if Qi intersect this was equal, then it would not be an irredundant primary decomposition. So we can always choose this. These are called splitting polynomials. But we'll never really use that term except sort of in our minds. Okay, so then we know if you just do the colon ideal of all of this with respect to Fi, colon Fi, well, it's going to be equal to the intersection of all these things, colon Fi, Qj colon Fi. But this is all j, and that's equal to Qi, because Fi is not in Qi, so it's exactly equal to that, and otherwise it's in. Yep.
So what's Q?
Q is I, sorry. So I colon that is the intersection of all these colon that, which is the intersection of all of these things, just by looking at the definition, and therefore this is Qi. And so by doing an ideal quotient with respect to some element, I get that that's equal to that. Now, if you want, maybe I shouldn't. Maybe this is not. Maybe I need to take it inside the intersection of the primes minus that. But anyway, this is still going to give us all of them. Okay. And the third point, this is true in general, that the radical of I is the intersection of just all the primes here, which is the intersection of all the minimal primes. But here, all the primes are minimal, so this is giving us this P1 intersect PR. Okay. So really what we want to do is, given a dimension 0 ideal, we want to compute these things. We want to compute the minimal primes, that's the first piece of information, or maybe the radical is the first piece of information, who knows, one of these two. And then maybe after that we can figure out what the Q's are. At least that would be one way to do it. Yeah.
Back to the argument, is there
By the QIs, that I have to say, by the ideal I, yes. So now I have to say that this argument that I've given here might not be completely correct. I really want it to be in the intersection of the primes minus the other prime. Because the primes are unique, the Q's are not. So my argument here is a little weak. So warning. This is not complete proof. And mostly because, but if I took it inside of the intersection of these things and that, and then I do this, then it will work out. But then you have to prove that there is something in the intersection of these primes and that's not in that, and that requires prime avoidance, which I didn't really want to state. So I thought I had a slick way out of it, but I didn't. Okay. So this needs prime avoidance, which is a great result, a great set of results. I still remember when I first saw it, I said, oh, this is just trivial. And then I remember trying to prove stuff on my own, and all of a sudden it just wasn't working out at all until you actually use then prime avoidance, just let it go through. It was great. But in any case, this is it. So basically, so we want to prove, we want the radical, the primes, and the primaries. So how do we get all that? Before doing this, I want to say something. I want to do a little word about field theory or about fields. We already said a little something about how if it's not perfect, then there's some issue, or if it's not that. But what fields are we interested in? Well, this is a kind of subjective question, okay? All of us might be interested in very different questions, but in particular, one can imagine that one is interested in Z mod PZ, which is FP, or maybe FQ, where Q is a power of P, and certainly the rationals, okay? These are like, these are the prime fields, and then maybe some other finite fields. Those are all pretty good. We also might be interested in fraction fields. So if we have K, we might be interested in K adjoin a variable T, or K adjoin a whole bunch of variables, T1 up to say TL. Those are fraction fields. We also might be interested in finite extensions. So like number fields. So we have Q contained in Q of alpha, which is Q adjoin alpha modulo some polynomial f of alpha, I guess. Okay. Yep.
F sub Q. Finite.
Yeah, this is Q equals P to the n. So this is all finite field. Yeah. No, these are finite fields. So there are two ways one can organize it. First, take the prime fields, and then take all finite fields, and then take fraction fields, take number fields. Number fields are, you would think, are significantly easier than fraction fields, but that's not 100% true. And so number fields or other extension fields, other finite extension fields. So this is, I should write this is really Q adjoin X mod f of X, right? This is and then we let alpha be just X in this thing, and that's a field if f for f of X is an irreducible polynomial. Okay, or other finite extensions of fields. Now in Macaulay 2, some of these are not as well implemented, and I want to change that, but that's the way it is at the moment. These things are all pretty well implemented. These are all pretty well implemented. These are sort of implemented, and so on. But what does it mean to be implemented? I mean, what is it we want? So what can we compute? So let's go back over here. So let's call a field K computable if the following kinds of things hold. This is kind of not a mathematical definition. It's a question of whether we have algorithms for doing things. One of them is we can compute A plus B, A minus B, A times B, and A divided by B, at least if B is non-zero here, and for all A and B in K when defined. Okay. I guess we also want to make sure that this is kind of stupid, but that we can represent the 0 and 1 element. Okay, we probably want ways of representing other elements too. But for instance, for the reals, we have no way of finitely representing it, just not. And also for the complexes. So so even though we can't really compute in those fields in some ways, but we can from this definition. If I give you elements, we can do these things. Okay. So anyway, so we have this, and 0 and 1 you should be able to tell. You also want to be able to compare two elements, compare for equality. You should be able to determine if A is equal to B. Okay. So in particular, you should be able to tell if an element is 0 or 1, which sometimes is completely non-trivial to do. So anyway, you have that. So these things are pretty well implemented for anything that you could, when I said it's not implemented, anything you could write down in Macaulay 2, you can easily, all this stuff holds, no problem. But that's not what I really mean when I want it to be computable. If you think about it, all over the place, we're going to need to be factoring elements and things like that. So what I want is the following. I want to say the third one, which is the key point, is we can factor polynomials. E.g., so if I have, not e.g., i.e., this is the whole thing. If f is in K adjoint, I'm going to do it as multivariate. I don't see any reason not to, but if you can do it for univariate, you can do it in this case, but it's a little bit annoying to try to do that. So if this is it, now note, this is an aside while we're in this thing. Note that K of x1 to xn is a UFD. So you can factor completely. So what I want to be able to do is I can factor it completely. So I want to write f is equal to a constant times f, yeah, I guess I'll call it f1 to the m1, f2 to the m2, to fr to the mr. So we can, if that's we can compute this where C is in the field K, F1 up to FR are irreducible polynomials, which makes sense since we're in a UFD. Okay, and oops, I didn't erase this one. Let's say irreducible and monic polynomials. Actually, no, we don't even know what monic means. Pairwise disjoint in the sense of the following. I wanted to say monic. If I had a monomial order, I could actually do that. Okay. But since I didn't give myself one, pairwise disjoint means the ideal of Fi plus the ideal of Fj is always equal to R. You can always find a 1 inside. That's not true. Shoot. Wait a second. Rats. And no two of the FIs are scalar multiples of each other. So I guess that means that Fi, the ideal of Fi, is never equal to the ideal Fj for I not equal to j. Okay.
Why was the first one you wrote false?
Because if I take if over a multivariate field, I might be factoring x times y to be x times y. X and y are the two things. But when I look at the ideal generated by x and y, I don't get the unit ideal. So I got tripped over by, so that this is how you tell if they're scalar multiples of each other. Okay, but this is the key thing. Can we do this or not? And so in Macaulay 2, so K equals FP, Q, and FQ, and fraction fields are computable. And simple extensions are sort of computable. It might not be completely as you might have to do something special to get it, but simple extensions K adjoin X modulo f of X, which is a new field L, are also computable. But you have to write it as a simple extension. So if I do towers of those things, I don't get it unless I can write it as a simple extension. So simple extensions are primitive extension. I mean, generated by one element. So over a characteristic zero field, you can always do this. So that should be sort of okay. But anyway, there are complications. It gets much harder the more complicated the field gets. Does this make sense, what I'm saying, basically? So this is the key thing. We need to be able to factor. In Macaulay 2, we can do it this way. Yeah. What we will assume that we have a that we're working over one of these things and that we can factor completely, because that's done directly in Macaulay 2 at the moment without any extra effort. Now, to say something about where do perfect fields come in? And there's one place that we really care about it. So, there's the notion of perfect field and separable field extension. So that's a K, and this is a K contained in L. Okay. I'm going to have you look these up if you don't know them, but because we don't really need them too much. But what field? So perfect field is pretty easy. It means that all, if I take a, how do I want to say it? Basically, it means that in both cases, it has to do with polynomials over K of K. And if you do an extension field, that irreducible polynomials remain irreducible. So the question is, when does that happen or not? So anyway, you can look at the wiki page for this. And for now, we will assume that K is perfect. And what does that include? i.e., K could equal FQ for any finite field, or Q, or actually not just Q, but any characteristic zero field. And the ones that are not perfect is this. So not perfect are fraction fields, are e.g. f of t. Okay. So these are just a couple little comments. And what we want is the key point of using this is that if K is perfect, then and F is in K adjoin one variable X. Okay, this is a univariate polynomial. One variable. Then we know that F is equal to some constant. Actually, let's say monic here. Then F is equal to, we can factorize it as F1 to the M1 dot 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 FR to the MR. with mi greater than or equal to 1, fi irreducible and monic. Okay, so I can do this. If this is monic, everything's monic, we don't have to worry about constants. So if this is the case, then what do we have? Then we define the square root of f to be get rid of all those powers, f1 to fr. Okay, this is the square free part of f. So is this okay? So if we have powers like x minus 1 cubed times x minus 2 to the fourth, this is just going to be x minus 1 times x minus whatever I said, 2. Okay, so we have this thing. Well, that's all very well and fine. So the question is, how do you compute this? You know, I probably should have said that we could compute GCDs in here too, but if we can factor polynomials, we can certainly compute GCDs. So so at any rate, especially in one variable, then the fact is that so if k is perfect and that f is equal to this is not really requiring. I'm going to change this around a little bit because this is I screwed up the statement. So if this is the case, k is any field, then this is the case, and we define that to be that. That works for any field whatsoever. And now the easy fact / exercise is that if k is perfect, then if I take then statement 1 is that the GCD of f and f is in k of a single variable x, say, that GCD of f and its derivative, remember its derivative is totally well defined even if it's over any field whatsoever. You just do the algebraic way of defining it, that the derivative of x to the r is r times x to the r minus 1. So we can take the GCD of these things, which all happens inside of here, which we can compute, that this is equal to 1 if and only if f is equal to the square root of f. In other words, it's square free. Okay. And the second thing is that in general, the square root of f is equal to, if it's not equal, then in fact it's equal to f divided by the GCD of f and f prime. Okay. So these are the things we want. We're going to want, so since we're trying to figure out the radicals, right? We're trying to get rid of these powers. So we want this element here. And so if k is not perfect, then we have some problems. And we can deal with that. But yes.
I think you said
So-
if k is perfect, then an irreducible polynomial over k stays irreducible even if you extend the field.
That's right, exactly.
So it's like a bunch of
That's right. And that's not one of them?
and the first, yeah, that's not, but it says every irreducible polynomial over k has no multiple roots in any field extension, which to me says it could become reducible over a field extension. It'll be square root.
Yeah, that's actually yeah, that's not true. I mean, that is true, but you can prove that there's only going you can't have a polynomial. Well, let's see. Actually, so if it's irreducible, like x squared minus 6, that factors as x minus root 6 times x plus root 6. But that has that doesn't have multiple. That if it starts off irreducible, then what did I say? If it's irreducible, yeah, no, that's exactly right. I screwed up. I meant you want that it has no multiple roots. Okay, I should have just written the whole thing down instead of trying to say it incorrectly.
That's perfection purpose.
Yeah. So that is it. So in fact, so Yeah, let me not write it down. I'll let you do it. Yep,
Sorry, is F prime in K of X?
yes.
Okay.
So what is F prime? I mean, if, so e.g., if F is equal to x cubed plus 3x plus 2, then F prime is just 3x squared plus 3, just like you would normally do it. And it's actually kind of wild that, and this is over any field. Now, what does that mean? So what about if it's what if it's characteristic 3? What is the derivative? So this would be x cubed plus 2 then, right? What is the derivative in that case? So this
That
is
is the derivative. Okay.
F prime is the derivative. Yeah. So F prime is equal to the derivative. F. Okay. But it has weird properties in characteristic P. Yeah, this 3x, if in characteristic 3, that will become 0. In fact, this thing has 0 derivative. So you have non-zero polynomials that are not constant, that have 0 derivative. And this causes all sorts of problems. It makes the field of characteristic P algebraic geometry interesting. For the rest of us, it's just like kind of a little annoying that you have this going on. But if it's and anyway, but so that means if this is Z, if F prime is 0, the GCD of F and 0 is F, right? So that can't possibly, that won't be 1 usually if in that case. So this is why we have yeah. So if it's not equal to 1, that would mean that F is not its square free part, and that will not be the case. If it's perfect, then it will. I'm saying this poorly. I don't want to make such a big deal of it, but I just want to say that we can actually calculate this part here in the fields that we're interested in. That's really the main part. So from here to here is just a single GCD computation to get that. Yep.
And I guess like part 1 there is literally saying like there can't be multiple.
That's right. So in fact, actually, it's not that's right, exactly. So so in fact, if I write F as a product of all these things, and I use the Leibniz rule, which does work with this derivative, and I do it, and I take the GCD, I'm going to see that almost everything is still going to be in there, except for 1 copy of each one of these things. Unless it's 0, in which case I might even have more copies, which makes it so, but it has at least that. So so yeah, great. And it's worth an example to see why this fails, right? If I take the derivative of this, I get 0, and the GCD of 0 and F is F, but nonetheless, this is still square free. But so but you don't, it is square free, but morally speaking, you don't ever want to consider it square free. So so that's somehow why we'll be able to get away with that kind of thing later on. There's a nice paper, by the way, that talks about dealing with extending all of these results, which were all done for perfect fields. And Becker Weisfeld, everything's perfect all over the place. And there's a nice paper that explains how to do the stuff outside of the perfect setting. So that would be a really great. I was going to try to do it in class, but I don't think we'll have time. So that would be a great project also, if anyone's interested. And I can show you the paper. It's a pretty well written paper. Okay, so now that was our aside on fields. So the basic idea is that that we care about factoring polynomials, and so that's why we're considering that. We do always use the fact that the polynomial ring is a UFD. And then the key point is that for univariate polynomials, we can easily do this if K is perfect. Okay, so now we're going to consider the case Eventually we will restrict to K perfect for now, but as I said, there's these results that allow us to extend that. But we want now, so given I zero dimensional, how to compute these things. So over a computable field. How to compute the radical of I and the minimal primes. And maybe the primary ideals too. Okay, we don't have embedded primes anymore, so we don't have to worry about that. Okay. So actually, I think I stated this slightly differently in the I guess not. Okay. So the first lemma or proposition is the following. So so proposition. This is actually true of any ideal. If I is contained in R, is an ideal, and F times G is in I. I don't think we did this last time, but if FG is in I and F and G are sort of co-prime, and I mean that I take the ideal generated by two of them, I get R. That's not the same as like if I take X times Y, the ideal generated by them is XY. It's not the whole thing, but in one variable case, that will be the case. So if this is the case, then I is equal to I plus F intersect I plus G. And happily, I don't have the proof written down here, so we have to figure out together. So do you see this right off the bat? Takes a little while to parse it. But anyway, so if we have an ideal, this is going to allow us to split things. And if FG is equal to R, every element, every prime ideal in here is going to contain F. Every prime ideal of this is going to contain G, and it can't contain the other one. So this is going to be complete. If I do a primary decomposition here and a primary decomposition there, I can just throw them together and it will be nicely irredundant because they can't possibly interfere with each other. But how do I show this? Well, I'll do the easy side. That one. Okay. So I is certainly contained in both of those. So that's okay. So the question is how do we go the other way? So suppose that I have an H is in I plus F and it's in I plus G. Okay. So one way to say that is, well, it's in this. So it means A is equal to A. Let's say A1 plus B1 times F. Okay. Where here A1 is in I and B1 is in R. This is a very general fact. This is for any ring. Oops, sorry. Let me write up here instead. And H is also equal to A2 times F plus B2. No, G. And I also screwed it up. It's A2 plus B2 times G. Okay? Where A2 is in I and B2 is in R. So we have these two things, A1 plus B1G and A2 is equal to B2G, and we would like to show that H is in I. So how do we do it? Yes, sorry, one of them is F. Sorry. Yeah, thank you. let's see, do I have it all right now? A1, so it's an element of I plus an element of F, so that's okay, and I plus an element of G. And I really want it to be just an element of I. But now we really need to use this fact here. So note, there exists a U times F plus V times G is equal to 1 for some U and V in R. Okay, so it's a partition of unity, basically. And so now what do? Actually, wait a second. This is really easy, but I don't see it right at the moment. So wait, what is it? What is the So if I take this thing, oh yeah. So if I take, wait a second. Oh yeah. So if I take so H, oh yeah, that's it. H is equal to H times this, right? So that's U times F times H plus V times G times H. Now, if I take this whole thing, I claim that that is in I. Now, why is that? Yeah, because if I multiply this by F, that certainly stays in I. And now I have F times G, which is in I. So note that F times H is in I, and G times H is in I. And U and V are elements in I. That implies that H is in I. Okay. That's the end of that. So it's worth while doing this because this is what all of the almost half the techniques are based on for zero dimensional. So H is equal to this, right? So if I take F times H, I get A2 times F plus B2 times G times F. And G times F is in I. So it's a sum of two things in I. But you're right, that was an extra step that I didn't write down. Okay, now let's suppose that we have an ideal I. This is in so remember that we have this situation that if I is zero dimensional, it has all these univariate polynomials floating around, one for each variable. So suppose I is zero dimensional, and F sub I of xi is equal to, so first of all, and F sub I of xi is in I, okay, for a specific I. So fix I, and then take that, and then factor this. I don't want to, I'm only doing one of them at a time, so I don't want to have double indices on this thing here. So this thing will have to factor some constant times some irreducible polynomial to some power up to PR to the MR. These are all of xi. So, and the P1 to PR are irreducible. And that if I look at the ideal generated by PI and PJ, I get the unit ideal, which is it's equal to K of, actually it depends where we're taking the sum, but it has one in it. So this is going to be equal to the ring R. Okay, so it has one in it. Yep.
Sorry, I think I missed 1 and 5. It's just a polynomial.
So and choose a polynomial in I, but only involving xi. So I could think of it as inside of here. So choose some polynomial fi inside of there. I could choose a generator. So if I take this intersection, there will be one smallest one, but maybe might want a little flexibility to choose something else. But in any case, it doesn't matter. I take sub element in here and I can factor it, and I can certainly factor it so that the sum of two of these is R. That's sort of the GCD is equal to 1. In the univariate case is the Bazoo thing that says that there exists U and V such that U times this plus V times this is 1.
Why subscript?
Yeah, you're right. We don't need that. We will need that when we start dealing with lots of them, but right now we don't need it. Okay.
We want monic for all the PIs, or it's not matter?
Doesn't really matter. I would probably prefer to make them all monic and just make it clean, but I think for the statement it doesn't really matter because we're always going to be looking at the ideal generator about one of these things. It doesn't matter what the constant you throw out front is. Then the proposition is the following with this notation that if I want to, I can start splitting it up. I get I is equal to I plus the ideal generator by P1 to the M1 intersected with all the others, and I plus PR to the MR. This proof is exactly that. It's just doing it 2 at a time, right? So if all these are satisfy this, then P1 with all the others also does, just the whole univariate polynomial thing. So the proof is use that the GCD of P1 and P2 dot PR, maybe of the M1s, I don't really care, equals 1 implies that there exists U and V in R, and actually in just one variable, such that U times P1 to the M plus V times the other guys is 1. Okay. And then consequently, we can apply that and split it up into 2, and then we just keep going. Okay. So that's the proof. But this is pretty good. Also, it's exactly what I said. If I now take a primary decomposition of this, it will totally not interfere with any of the other ones. So all of these will just do their own thing. Usually when you add in elements to I, it fractures awfully and you get lots of non-minimal components. But since everything is sort of maximal idealish here, that there's no room for such things to occur. So this is a really good thing. So whenever I have one of these univariate polynomials, I can just split the ideal. Oh, shoot, this is quite a bit longer than. Yeah.
We're not working over perfect field for either of these, right?
Nope, no perfect field needed for this. So this all just works. The problem is that the following thing does not work. So I'm going to do a couple more things before we take a break, and then what I want to do is yeah. You always spend too much time on some of the stuff. So in other words, we can assume, if we want, that I intersected with K of Xi, which will equal some Fi, and Fi is an irreducible polynomial. Okay, because if it's not, we just split it using that stuff. So then we have that. So we have a situation that and this is assume that this is the case, and then we can assume this for all I equals 1 to n. Okay. So that's kind of a cool thing. But here's another cool fact that is really important, that is very closely related to this. So let K be, and this is Seidenberg's lemma. (1974) lemma, this paper is kind of ridiculous, lemma 92. So, okay, it goes through, basically it's showing that you can, it doesn't actually really care about computing things, but it's showing that a lot of commutative algebra is effective over polynomial rings. And here he's showing that in certain cases, computing radical is effective. So let's let K, or assume K, let K be a perfect field. Let for I from equal to 1 up to n, Fi being K of x of I intersect I, and where Fi is non-zero. Okay, it could be happen that this is equal to 0, but then that tells you right away that I is not zero dimensional, because at the very beginning that linear algebra thing we had proved that it had to be finite dimensional. Okay, so we have for every I from 1 to n, we have this thing here. Okay, then we let G sub I, by definition, we let it be the radical of Fi. This is the square free part of Fi. And that is something we can compute if it's perfect by doing this over here. Okay. Then the really cool thing is let Gi be this, then the radical of I is equal to I plus the ideal generated by all these guys. So we can get it with no extra effort right off the bat. By the way, what do you think? If suppose these are all irreducible polynomials, okay, does that make the ideal a prime ideal? That would be really cool if it did. By the way, this proof I'm going to leave as an exercise. Really what happens is that what you would think about it is if I take R modulo this stuff, that actually is sort of like a tensor product, K of x1 mod this, tensor K of x2 mod that, and so on. And that really hasn't, that because these are irreducible and it's perfect, they have no nilpotent elements in it. And then when you mod out by I, further than that, you still get no nilpotent elements in it. And that's what R mod that is. So so it's not such a hard proof. It's a little annoying to write down. Here's an example. K is equal to Fp adjoin T, and I is equal to x to the P minus T, and y to the P minus T. K is not perfect, but it is the case that both of these are radical ideals. But the radical of I is not equal to I. And you can sort of see it just from this thing here. If I subtract these two elements, I get x to the P minus y to the P is in I. But since I is over characteristic P, this is equal to x minus y to the P. And so therefore, x minus, can you actually see? Oh yeah, you can. Okay, good. X minus y is in the radical of I. So radical of I is not equal to I. So this is the cautionary example that you always have to do whenever you're proving things about anything like this. If you leave out the word perfect, you have lots of things, you have to somehow deal with this. But this is actually a somewhat of a serious problem. How do we actually find it? This is an example of one where that if these are both irreducible, but we don't get even radical, let alone prime. However, what happens if it's nice perfect field? Maybe, what do you think? How optimistic are you? Do you think that it will be the case that if those are all irreducible, that it's a prime ideal? What could go wrong, right? It is called perfect. Right. That's I and the beholder, I guess. So here's an example. What if I take I is generated by x squared minus 5? And y squared minus 5 over q, say. That satisfies that the univariate polynomial for x and the univariate polynomial for y are both irreducible. But you can sort of see that there's something else going on here. So, but x squared minus y squared is in I. That implies x minus y times x plus y is in I, but that's not the case here. So if so this thing has two prime ideals associated with it. And that's one of the last thing we have to really figure out for that case. Why don't we, I suggest we do the following. We take a break and then I want to do one more thing. And then we're going to try together at first, and then I'll have you guys try on your own to actually solve one of these kinds of things. But we need one more thing before we can do that. So, but I think it's time for a break now before we do that. So what we're going to talk about next is what happens in how do we actually handle this kind of case when we have irreducibles, but it might be much more complicated. There might be other polynomials in there too, who knows? But how do we actually handle that kind of situation? And it turns out to have a pretty cool solution, pretty easy also. And once we have that, then we can actually go to town trying to do some of these things. And we'll do it by computer after that. I'm still interested in going through the maximal independent set stuff, but we're going to do that after playing around, I think. And but we'll play around together first. Okay, so let's take a 10-minute break now, and then it'll take another 10 or 15 minutes to show this stuff, and then we'll play around with it for probably most of the other time. Oh, yeah, we should probably get started again if that's here, let me get my computer out. Okay, so I won't be using that yet. So in fact, first what we'll do instead is I want to say what happens, how we deal with the fact, like this example, start over here. Might need to move that, okay. So an example would be x squared minus 5, y squared minus 5, containing q of xy. This is a by hand one, and this is not prime. But we want to figure out how to make it prime. Okay. And the idea, the reason it's not prime are where are the roots of this thing? The roots are plus or minus root 5 and plus or minus root 5, all separate, it can be any one of the four things. So if I think about it, where are these points? Here's root 5, it's these 4 points here. Okay. And now when you intersect with a variable, what are you really doing geometrically? Projecting. So if I intersect here, this is the x coordinate. If I project down here, I'm really intersecting with q of x, and I'm getting two things here, which is x squared minus 5. Okay, and if I do it to the y, I'm getting two things. But what if instead? So the idea, which is a good idea, is that the two coordinate projections never will separate these points out. So it can't possibly figure out that there's different things going on. But what if instead I choose another axis, just some weird axis like this one, okay? And now I project onto it perpendicularly. I get 4 points. So the idea is we want to choose a coordinate system so the last coordinate or the first coordinate, any particular coordinate we want really. So the last coordinate of all the points, last coordinates of all the points are different. So in other words, if this is my new x-axis and I project onto it, you can see that all the coordinates would be different. And so now let's do that as a definition in general. Let's let I be contained in R, our usual polynomial ring, be a zero-dimensional ideal. And suppose the zero set over the algebraic closure of I is a whole ton of points, which I'm going to write as A, the first point is going to be this thing. Oops, to A, one, A sub n. Okay, that's the first point. And dot, 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 and then the last point is going to be A1, say D points, which may or may not be the, yeah, that's a comma, and then this is another point, and then this is the set. So suppose this is it consists of D points, and these are the D points, but over the algebraic closure. So these things are all probably somewhat hard elements to compute sometimes, but at least theoretically we have them. So then we say if the ith coordinates say if AI1 dot 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 AID are all distinct, are all pairwise distinct, different. We say that I is in normal position with respect to, WRT is just with respect to XI. Okay, so that's our definition. And so the basic idea is that this ideal is not in normal position with respect to either variable X or Y. But if we change coordinates, it looks like we can probably get it in that form. That might not need some proof, but at least that looks like a reasonable thing. And now here's the so here's the proposition. Remember, we're assuming that K is perfect here. Again, there is a way around that, but would have to think about it. Okay, so and now if I is in normal position, with respect to xn, I'm just choosing one of the variables, so it's convenient to choose the last one a lot of times. And I is radical. Okay. You know, if the field is perfect, we have no trouble with that because that's this result over here. We just add those polynomials in, which is actually an easy process, a bunch of GCD computations. Well, we have to figure out those polynomials Fi, but that's actually linear algebra in R mod I if we really don't want to. We can do it via Gribner bases as well, or linear algebra. And the GCD we could also do by either Gribner bases or linear algebra. And so that part is not so hard to get in this. And it's typically, that part is never if you have a bottleneck getting that information, you're screwed is what it comes down to. So anyway, that's one thing. And then, but if it's in normal position with respect to this and this, then for the Lex order, lexicographic order, x1 is greater than x2 is greater than dot 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 is greater than xn. This is a strict lexicographic, no degree things in it or at all. The Gribner basis of I, this is the reduced Gribner basis of I, is of the form turns out to be of the form x1 minus g1 of xn. Did I say it's in normal position? Yes, I did. X2 minus G2 of xn up to xn minus 1 minus Gn minus 1 of xn. These are all the last variable, and then G sub n of xn. So this is the Gribner basis, each one of these, this set of n polynomials, where what it holds, where the degree of G sub n is equal to D is equal to the dimension of R mod I over the base field K. remember, we also said that since I is radical, this dimension is the number of points also. I mean, in reality, what would in that case, what will the polynomial be if I change coordinates and call that, say, x prime or something like that? What will the degree of the intersection of that, of the ideal with that line be? And there's going to be 4 points on it, right? So it's going to be a degree 4 polynomial that's they're just different points, and that's going to be the dimension of that thing. So basically, that's where this is all coming from. We're going to get a polynomial of the degree of this. By the way, this is well, anyway, so there's that, and the degree of each g sub I is less than or equal to d minus 1. That is not specifically difficult, because if I have some arbitrary polynomial here in xn, I'll have to reduce it with respect to gn anyway, which will make it degree small enough, like a degree d minus 1 or less. But what's cool is that these all appear linearly, and in fact, you can see all the solutions in. You find all the roots of this guy, and you just plug in those roots into these polynomials, and it tells you exactly what each of these things are. So this is called the shape lemma. And this is in I don't know why it's, I mean, I know why it's called the shape lemma, but it sounds kind of funny saying it, but it's because it's got a nice shape. So anyway, we have that. No, and yeah.
The shape of the Grosvenor basis, since the original shape lemma is as nice.
Yeah, that's right. It has a staircase thing, and this is like the shape of the staircase and so on. Yeah, no, it's not like in Lie theory when you have the killing form, which you always thought was the annihilator thing, but it's really from Professor Killing. So anyway, so that was kind of fun. I thought the professor was joking when he said that, and but he wasn't.
How much of the lex would matter here? Like if I swap x1 and x2, is g1 and g2?
Doesn't matter at all. So what matters is that I could take an elimination order as long as xn is last. So in this order, I will get something like this. Now, what happens if I change the order? Actually, I can make, as long as I make x1 to xn minus 1 greater than anything in xn, then these will be lead terms. And this will have the same lead term. So there's not much going on. I mean, I have huge leeway of what monomial order I could choose here for this to work. Now, notice that you can tell whether, if suppose I get this and I get some polynomial here, you know, or suppose I just have this univariate polynomial, which I can get from the very first thing we did today, right? So we just look in the thing, we take the equation we take all those elements and figure out its linear dependence, and that gives us this thing. That gives us the degree D. This dimension we can calculate from any Grosvenor basis essentially that we want, and in which case we can tell if those are the same. And if they are the same, that means this is going to be degree D. But that means that these lead terms, if I choose this order, are going to have degree 1, because if it were larger, the dimension of the quotient would have degree larger than that D. So it's kind of anyway, unless there's some smaller degree thing in here, but if that's the smallest generator of that, then that's not quite a proof. But the point is that you can act in some reasonable way, you can tell whether it's in normal position or not. Okay, well, and then here's the corollary of that. If it's in shape position, if I is radical and in shape position, and I should say normal position. And in normal position, with respect to xn, and as always, k is perfect. So if G sub n, that polynomial down there, is equal to, well, it's going to be square free since this is radical. Alright. So this is going to be P1 times P2 dot 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 to PR, and the P sub I are irreducible and pairwise coprime basically, pairwise different ideals. So, you know, just like we were saying before, so these P sub i's are pairwise different. So if G sub n is equal to this, then the radical of I, well, that is I, sorry, that is equal to I plus P1 intersect dot 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 I plus Pn is an irredundant primary decomposition of I. And how do you know that? How can I tell if I add P1 to this and that's irreducible, then what do I have here? I have all these equations plus an irreducible guy here. If you think about it, because those are all linear, we can get rid of those variables and I mean K. So just note that K of x1 to xn mod I, actually let's do I plus P R, P sub I. What is that equal to? That's K of x1 to xn mod, and then we have these equations here, x1 minus g1 dot 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 xn minus 1 minus gn minus 1. Those stay in the ideal, and then the P sub I is in the ideal as well. Okay, so we have this. But so how do we tell if this is a so all the P's here need to be, and that's what we're looking at. We're looking at one of these things. All of them have to be maximal ideals. So how do we tell that if an ideal is maximal? We tell that determines, that's if this is a field, right? But this thing is isomorphic as rings. I can get rid of this says I can just remove x1 to xn minus 1, and this is going to be isomorphic to K of xn mod P sub I, which is a polynomial in xn. Because I'm taking one of the factors of it. So I'm taking I plus that. So the Gn will be a factor of, it'll be what? Yeah. So it will, if I put it, I could put Gn here, comma Pi, but then I don't need the Gn. But this thing, Pi is an irreducible polynomial over this. That makes this a field. So, so this is a field. And therefore, I plus each P sub I is a maximal ideal. And then we're done. Okay, that is the primary decomposition. You can then, that's corollary 1. Corollary 2. If okay, if K is separable, sorry, is perfect. And radical of I is in normal position. That might be a little harder to figure out. With respect to xn, okay? And f of xn is in I intersect K of xn. Satisfies, and now we factor it. F is equal to P1 to the M1 dot 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 PR to the MR. I don't really care about the constant out front. We can put it in if we want. Maybe I should put it in. And it satisfies this. is the complete factorization, which means all of these things are distinct and so on. Complete factorization. I should have just defined that in the first, so I don't have to keep tripping over it. I kind of forgot that I'd have to do that. And so each of the piece of i's are irreducible. So each piece of I is irreducible. But it had to be a normal position, which is something that we only know about after we've done the radical. But at any rate, so in this case, then the ideal I, which is zero dimensional, so I is zero dimensional, then I is equal to Q1 intersect QR. That's the same number as here, where QI is equal to I plus, well, remember the prime itself was I plus the p sub, where is it? Up here, I plus p sub I. And now all we have to do here is take the p sub I to the mi. And this is pi, which is I plus pi primary. And now we're really at the point where we've got the whole algorithm for zero dimensional. So should we actually summarize it a little bit, maybe? So why is this true? Well, this is true because whenever you have an element like this, you get an intersection like this. Okay, so then we will get that is equal to the intersection of all these guys, just period. And these things are all square free, co-prime with each other, so that if we have a primary decomposition of each one, we can just put them all together, just like we did before. Now, what's the primary decomposition of this? Well, if I take its radical, it certainly contains I plus pi, but we already just showed that that is a prime ideal, and so a maximal ideal, in fact. So in fact, that's it. We're done. Okay, so let's put this together. Now, there's a number of steps here, and it is not 100% clear the best way to put these together. Okay, so in fact, I'm still not sure that it's always been put together in the best way. There might be new things to learn and how best to do this, because each time you have different ways of doing things, and sometimes one of them is really much slower than another, and so you have just interesting situations going on. So the input will be an ideal I, zero dimensional. Okay, and we want to find, maybe we want to find all three things: the radical of I, P1 to PR, and Q1 to QR. Okay. So how would you do it first? What would be a good way to go about doing this? So I'm actually asking because what I write down might not be the best one, okay, as I was saying. It seems as a rule, we could immediately figure out, we could calculate I intersect each k of xi, and then figure that out and calculate that element. And that will give us the radical right off the bat. Okay. But in fact, sometimes it's actually easier to not do that all at once. And so I would first split I as much as possible. So for instance, and this is again hard to tell. So if, for instance, f1 of x1 is in I intersect k of xn, k of x1, okay, and then I can write f1 is equal to some constant, which is not relevant, times p1 to the m1 to pr to the mr. Okay, so we have something like this. Each I will have a different polynomial totally, usually. Then certainly I can, if I'm interested in the radical of I can just replace this with the product of all these things. But what I might want to do, yeah, actually, how do I want to say this? Let me actually say the simpler way first, and then I can talk it through a little bit more. I'm going to get rid of this. So the first one is to compute F1 up to Fn, where Fi is in K of X I intersect I. Okay. And then compute the radical of F1. For the radical of Fn, this is K is a perfect field. Okay. So we compute these things, and then we have that the radical of I is equal to I plus these guys here. Radical of F1, comma, dot, 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 radical of Fn. Okay, so that we've computed now the radical of I. I think the thing to do next is to compute the p's. So that just means computing a primary decomposition of I. So now we want a primary decomposition of radical of I. Okay, so we've each one now is down to this. So that's going to, so 2a, I guess. I don't know how to write this exactly. This is just what we want. And what we could do is we can take, we can just split this up. F1 might have 7 factors, so we just drop this into 7 different ideals. Now, here's the trouble. Suppose and this happens in one of the examples that I'm suggesting, I think. Suppose we're in like 5 variables, and we have a f that has 10, and it's the same, essentially the same polynomial for each one, because it's a symmetric thing, and there are 10 factors to it. So how many splits do we have then? We would have to do each one of these 10 times. So we would have 10 times 10 times. We would have a huge number of things, but it's not the case that that is necessary, because once we split 1, then it makes everything else simpler. So now I would do is I would split I until split I into a bunch of ideals. Intersect, say, I1 to IN, such that each I sub I intersect K of X, each I sub L in K of Xi, that's what we're doing, is irreducible for all L and all I. Okay. So we have all these ideals, and we just go through and we compute its polynomial like this. If you think about it, it's going to have to be something smaller than these things here. Okay, but anyway, so basically we have this, and actually this is splitting the radical of I. Sorry. So we're trying to find the primary decomposition of the radical. So we have the radical of I, and we have all this. So this is pretty easy. I just take, for instance, I take the first x1, and I take its polynomial, and I just split using that. Boom, 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 boom. And now I just throw that in again, and I sort of recompute a Goodman basis, which is usually a fairly quick thing at that point. And then I take the next, and then at that point, for every single one of those, the F1 thing will be irreducible, because I threw it in as irreducible somehow. And now I do go on to the second variable, and I factor it. For each one of these, I factor it, and I just choose, and I split it up depending on. All of those are necessary, right? Because every time I'm getting a irredundant decomposition when I split these up. So I first do this, with respect to our x1 first, then x2 on all of those ideals, on all of those ideals. And then I have a larger set, which I get rid of the first one. I just have now all the ones on x2 are irreducible for x1 and x2, and I just continue. And then I do xn on, then split via xn on all of these, all of the previous ones. This part is actually not necessary, but it makes your life sort of much better. Because first of all, it's much more likely that each one of those is going to be in normal position with respect to one of the variables. And it's pretty easy to tell when that happens. So what happens? So a lot of these you can just tell immediately are prime ideals. But some of them you can't tell because you have something like x squared minus 5 and y squared minus 5 in it, or maybe much more complicated where you really can't see what's going on. So then we have 3. So for each I sub I not in general position, how do I tell if it's in general position? Well, it's already I just computed Grosvenor basis of it. You've all probably heard that lexicographic Grosvenor bases are bad, right? I've even said that. But in 0 dimensions, they're not bad usually. Unless, I mean, you have to go up to whatever the degree is, so that could be quite bad. But yep.
Is that a feature, is that because no order is bad in 0 dimensions? Or is that just like, oh, actually in this one setting, Lex is chill?
It's because no order is bad. It can still be a little bad. If the degree is very large, you might be able to find a very much smaller Grosvenor basis. So if the D that we're dealing with here is small, like less than 1,000 or a few thousand, then it should. I mean, the polynomial you're going to get here, if you have 1,000 points and it's in not normal position, it's going to be of degree 1,000, which is a little less pleasant to deal with. But that's the nature of the beast. If that's how many points you've got, you got to get around it. This is one way to sort of try to split that down without having to do so much. So if you only compute f1 first, you can ignore the other variables almost. You just compute f1, throw it in, and now you just intersect with x2, and then you take the square free part as you go. So there's a few various things you could do to play around and change it a bit. Yep.
But because of the shape lemma, we're not allowed to be cheeky and use GrevLex or something like that?
No, GrevLex won't tell you what's going on. It'll just muck everything up. I mean, in this case, if it's going to have this shape lemma thing, you will not see that if you're doing GrevLex typically. So in that case, so for each one, what you do is you change coordinates, but you only have to make a very simple change of coordinates. Change coordinates. And I can show you how to do this in Macaulay too. You keep all the xi's to be themselves for I not equal to n, and you let xn go to xn plus a summation of c sub I x to the I for I equals 1 to n minus 1. And ci are in k, and they're random. Now, one has to prove, and this is one thing that's actually cool in the the Becker-Weisfennig book, is he actually shows how large the set of where you have to look at random things are in order for there to exist such a thing in here. So for instance, if you're in a very small field, you might not find anything, but that typically happens in small characteristics, 2, 5, 7, 3, whatever, but much higher, and just even 11, it's hard to find problems with that. But in any case, when you do this, you change coordinates and you just recompute a Grosvenor basis, and it will almost always be in normal form. If it's not, you change basis again. You just keep going until you get one, or if you keep a count, and if you can't get it after a while, then you give up or you try something else. Okay, so this is the general thing, and there's a lot of little things that you can do differently. So I thought we would get started with one interesting example, if we have, and then you can play around with it. The second file is week9.m2. It has some Macaulay 2 code and the example to try doing this on your own. But I do want to here maybe I'll do this here. I want to show you, tell you where these ideals that I'm writing down are coming from a little bit. Or maybe we should work on it first and then I'll tell you after that. Yeah, maybe we'll do that. So the ideals that we're going to be looking at here are going to be contained in K of x1 to x4, y1 to y4. And I is going to have a very specific form. It's going to be some polynomials. It's going to have f1 to f4. These are not in univariates at all. These are just, and maybe they're 5 actually. I think they're 5, but I think the sum of them is 0. So, and then you're going to add in x1 squared plus y1 squared minus 1. And up to x4 squared plus y4 squared minus 1. So really what's going on is it's coming from Kuromoto oscillators. Each xi is going to be the cosine of an angle, theta I, and the corresponding y is going to be sine of theta I. And then these are going to be some polynomials in xi and yi that are quadratic. And it's going to come about from a graph. But I'm not telling you what the graph is in this example. We're just going to do it. So let me share my screen. I'm just going to share my Emacs screen. Let me get a So what I'm going to, I kind of want you to sort of spend time doing this yourself. So we'll see how this goes. But here, okay, can you everyone hear me still online? And you can see the screen. Oh, that's way too small. Let me increase the size. Is that okay? Okay. I don't know if I'll be able to. Let me get. Okay. Oh, it's too long though. I have to make it a little shorter. Yeah, that's good. Okay, so I have written a handful of this we don't need. So I have this function in my init file for Macaulay 2 called C. It's C of an ideal. It just does net list of I underscore star, so it can just sort of display it out nicely. It doesn't work with the tech version so much, but at any rate. So and then I've written a handful of new functions. These first three, my denominator, my GCD, and my factors are probably not that important for the moment. But the univariate ones might be. So what this does is if you take a variable and an ideal, which is 0 dimensional, what it does is it uses the eliminate command to find that polynomial that we're talking about in one variable. So this finds a univariate polynomial in that variable in the ideal. And then actually I have this function instead. Factor is what I consider an annoying function in Macaulay 2. It's very nice. It gives you a nice description, a nice pretty thing. But if you actually want to use it in a program or further computation, it's just kind of annoying. So factors, what it does is my factors actually is it just takes a factorization and does it with the polynomial comma the multiple, the exponent, and for each one of those things. And then univariates does it for every variable in the ring, if you want to sort of get it. Okay. Now, what I'm going to do. Yes, week 9 is in problems, in the problems subdirectory. Ah, crap. It should be this week 9.m2 should be on the files in there. I'll make sure it's in the it is there. Okay, maybe I forgot to check it in. I thought I did, but I'm not.
I mean,
Yeah, I know, maybe I didn't push it.
Is to the Google Drive.
But it's also on slides.
Yeah, but I mean, there is the link for the Google Drive for surprise there. Without solve.
Actually, I think it's in there. I don't, it doesn't appear to be in my, oh, wait, no, I have to push it. Let me push it. Yeah, I think I didn't push it. The last, thing. Okay, anyway, so here is, so I'm loading this, I'm restarting. Oops, I'm gonna start Macaulay 2, and, I'm going to restart. I don't know why, just, and then I'm loading this file, but it's not finding it. That's because I called it something different. Week 9. Okay, so I do that, and okay, so I changed the name without doing that. Okay, problem A is you are supposed, and this is a homework assignment, but we're going to do part of it at first just to get going. So over this, we are going to take an ideal. We're going to do it over the rationals, although we can do it over a finite field too. Like we could do ZZ mod 101, for instance, or whatever. And it would even work over finite field, smaller fields, but I don't know. You have to be a little careful. So here is a polynomial ring in x1 to y4, which is in fact all the variables x1 to x4, y1 to y4. And now here's the ideal we're going to take. And I can explain to you maybe next time how I get this ideal. Okay, now if I do C of I, what does it look like? Okay, it looks kind of messy. It actually has a linear polynomial first. In reality, what I'm doing with this kind of thing is I'm setting one of the thetas to be 0. So that means that the xi for that is cosine of 0, which is 1, and the sine of 0, which is yi is 0. So it's just setting some variables. Anyway, so you get these polynomials. They're all very nice. Linear, quadratic, not only quadratic, linear in each set of the two variables. And then there's 5 of those equations. They all actually add up to 1 or 0 rather. And then I have my trig equations in here. And so the question is we want to solve this. Now from the Cornell oscillator thing, you also want to know which ones are stable points. It's a dynamical system kind of thing. But actually figuring out what the primary decompositions of these things is an interesting problem that is unknown still. Okay, we can do it for any specific one for small sizes, but even there, let's take a look at the dimension of I and the degree of I. Degree of I is going to be the dimension of that vector space if it's finite, if dimension is finite. And what is it? It's dimension 0. So this is a 0-dimensional ideal, and it has 36 degree 36. Okay, so one might expect 36 solutions from this. Okay, we can use the primary decomposition command in Macaulay 2. Actually, we can do more. We can do minimal primes maybe first. Minimal primes of I, and once you do this yourself, you're going to be a little discouraged because it does it so fast. But you do it and understand it, and then you can put it together as a function and do it that way. So if I do net list of this, how many are there? Oh my gosh, there are a lot of solutions. Okay, some of them look maybe pretty trivial. Let's take a look at them. Look at this. Y, all the 4 y's and a bunch of x's are plus or minus 1s. Whole ton of those. In fact, maybe all of them are like that. Nope. So there are some others. Okay. So, but it turns out that these ones are pretty trivial ones. So we have 2 options here. One is that we can just, we can just do that. But here is something where I say easy is this ideal where I take the squares of all these guys, and then I take all the variables y's. Okay. Now, if I do I1, I can do I colon easy. Remember that what that's going to do by the way you do colon ideals, that's going to get rid of if I have a primary decomposition, which I don't yet, that will remove all the ones that are supported on the set. So if I do I1 equals I colon easy, I get some ideal, which is kind of a huge mess. And if I do I colon that, I get I2. And now I can look and see if I is the intersection of those 2 ideals, and it is. Okay, and it turns out that whenever you do that, now I have two ideals that I can do the primary decomposition of both of them. We don't need to do this. I'm just trying to get rid of the trivial ones so we can ignore those for the time being. But you should take a look at it. I2, one of these is easy. What is I2? I2 is just this ideal with all the, so if I do C of OO, I just get all these squares. You should, by the way, make sure you know how to get a primary decomposition of that ideal. That's when you could hopefully look at and just see, but it might take, you can take a look and see. So the I1 though is the more interesting one. It is still dimension 0 as it has to be, but there's only 20 equations. We've gotten rid of 16 solutions basically. And now we want to figure that out. So exercise A1 is to try the functions univariate and univariates out. Here, actually, let me anyway, whatever it's and just try to take a look at it and see what they do. Okay, so we have this ideal I1. So why don't we do univariates of I1? Okay, and let's see what that gives us. Actually, it's pretty fast, but now I'm going to do a net list of it so we can see them all. So these are all the univariate polynomials factored over the base field Q. So the x1 has a factor of 2x1 minus plus 1, and then this cubic factor, and a degree 6 factor, and that's it, okay? So that means immediately, by the way, that since this is dimension 0, we are going to have those three things. By the way, is this a radical ideal? The first one, if you look at it, has only powers 1 at the end. Let's see if we can, and then this one has 2x1. This is also similar, 1, 1, and 1, okay? Do you see the ones are the exponents, right? So does this make sense, or is this too, so we have that one's all ones. Actually, if you look at them all, they're all going to be ones. I think that the ideal I is radical already. I1 is radical. So actually we can try Macaulay 2 is radical of I1, and it doesn't take it because there is no is radical command. We can do radical of I1 equals I1, and it's true, okay? So this one is actually, if I do radical of I equals I, it's also true. So this is a radical ideal, which means over the algebraic closure of the original ideal, there were 36 solutions, and now this part of it, there are 30 solutions. So now the question is, how do we find those solutions? And here, that's the exercise. Find a primary decomposition and the minimal primes for I1 and I or use I1, and then you get the other ones from the I2. So how do we do it? Should we do it by hand a little bit? So probably, oops, that's a later one. Should we do it together a bit, or do you guys want to play around with this on your own yet?
I wouldn't mind doing it together.
Well, let's do it together then a little bit. We're going to try I1, okay? So I'm going to do univariate of in variable x sub 1 of I1, okay? And I get these things here, okay? These are all of degree 1. We already know it's that. So we're going to do the file. What we're doing now is part 2A, okay? And then afterwards, we're going to have to see if we have any of those that need normal position or not. So how do we do it? I'm going to do the following. I'm going to say for fac in univariate of this list, and now I'm going to take I1 plus the ideal of fac is now going to be one of these two things, is 2x1 plus 1 comma 1, or this list here, or this list here. In fact, let's do it this way first. I'm going to do the list, and I'm going to print fac, okay? And it returns some lists, but it's here, it's at each part of the list, I'm giving it this, then this, then this. That's actually a useful way to see what's in a list sometimes. Okay, now, but that's what we would do first maybe. And then what we do instead is we're going to take this I1 plus the ideal of what? Well, facts, the zeroth part of fac is the polynomial. So I'm going to put sharp 0. Sharp is the indexing for there's two ways we could do it. We can do sharp fact underscore 0. That's fine too. So might as well do that. Okay. And actually, you know what else I don't have is I1. Maybe I should make I1. I should put it in lexicographic and put it into a lexicographic order. So in fact, why don't we we don't need that yet. Let's do this first. Okay. So I can do fact in there and list. I'm going to do I think trim will make it a little nicer. So here we get 3 ideals. So let's net list these and see what we get. Okay. Yep, we get 3 ideals. And trim, I think if it's the unit ideal, it would show you that it's a unit ideal. So we've just broken I up into these 3. So let's call this I1s. Okay, no, shoot, that's not J1s. Okay, this is after we've split by the ones. Okay, so now let's do intersect J1s, comma, that's just intersect. Is that equal to I1? Okay, good. It should be, but from the theory of it. Okay, so because we've just added these trim just simplifies the generators a little bit. Sometimes it simplifies them, sometimes it makes it harder. But here I think it probably simplified it. And now we have these 3. By the way, if I take J1s and for each one I calculate the degree, I get 2, 6, and 12. Wait, what was the degree I was thinking of? Was it 30? I thought it was, or was it? No, it was 20, right? The degree of I1 was 20. And now it's split it up into degree 2, 6, and 12. Yep.
So is the backslash or the slash
Slash forward.
Is that piping into?
Yeah, that's taking this list, which is 3 ideals here, and for each one it calculates degree, and then it returns a list of all the values. So in that would be like in Python a list comprehension kind of thing that you would do. Okay, so anyway, we have these 3 ideals. They add up to this. We don't know if any one of those are prime. Degree 2 is starting to get to be looking pretty prime. So let's J1. So what does the first one look like? That does not look prime to me. That looks like a humongo mess. Actually, if I do Grubner basis of that, what do I get? Oh, it's much nicer. But take a look at this. Let's do ideal of that. Oops. Well, that's okay, I guess. Is this a prime ideal? Can you tell by looking at it? Remember, whenever you have a variable that appears in it, or a linear one, you can take like the y3 and just remove it, because of this trick where you're going to get an isomorphic thing in one less variable. And y2 you can get rid of, y1, x4 you can make set to be a -1/2, x3 is, I mean, all these go away, but you're left with one polynomial of higher degree. Actually, let's do it by the Grubner. Let me do Rlex is equal to new ring of R with the new monomial order. So this is a way that you can take a ring and just change some aspect of it. So monomial order is Lex. And now I'm going to do for J in J1s. Okay, I'm going to substitute J into Rlex. Okay, and I'll call this J1 Lex. J1's Lex. I don't know. I'm really awful at naming things. So so if we do that, we get all these ideals. And now what we can do is compute a Grubner basis of each of those and see how far we've gotten. So we can do a Grubner basis of J1's Lex underscore 0. That's the first ideal. Maybe I shouldn't have called it something so awful. Let's call it K1 and get rid of the Lex. Or L1, L for Lex. And let's get rid of the S1. We'll just call it L's. So let's do that again. And now we do Grosvenor basis of L's underscore 0. And I'm going to make an ideal of the result. And I'm going to do C of it, just so we can actually see it a little nicer. Hopefully that'll work. Yep, here's what we get. We have x1, x2, x3, x4, y1, y2, y3, and y4. This is in normal position. All the other ones are linear. Notice this has a y2 plus y4, which is a degree less than that, as it should. And y4 is the last variable, so this actually is pretty good. So this one here is in normal position. That means we have to factor this thing here, but it doesn't factor over Q. Now, if we wanted to do this over the algebraic closure, we could factor that by adding in a square root of 3, like adding in a root 3 over 2. But anyway, so now let's do the second ideal and just see where we stand. Okay. Is this in, this is almost the normal form too. X1, X2, X3, X4, they only involve Y4s at the end. Y1, Y2, Y3, and Y4. That's the polynomial 6. And I think 6 was the degree of this thing, actually. So, but maybe that, it could be that this thing factors. So we wanted to figure that out. So I'm going to do univariate in Y sub 4 of LS underscore 1. Okay? And there's my polynomial. I think it actually factored it. I'm a little surprised at it because I thought. So that's the polynomial. If I factor that, then it is irreducible. Okay, so this is a thing that is over some extension 6 field of Q. This is going to define 6 points over that. So this one is also is prime because it's in normal position and has an irreducible final polynomial. How about this next one, LS underscore 2? Oof. Okay, this one, x1, x2, x3, x4, y1. Notice that all these things look like they're just y4s on the back. And these all look, this is in shape position already. I was thinking one of these wasn't, but in fact, I think that was a different example. Okay, so these are already all in shape position. The question is, we have to factor this guy. So let's do that. Let's factor LS underscore 2, find the univariate polynomial. Wait, was that really, let's go back to primary decomposition or minimal primes. I1. O / degree. Oh yeah, they're all prime. All 3 of these. We didn't need to split them up. But it's actually quite hard oftentimes to prove that something's prime. But in this case, we actually have a honest to God way of doing it. So this is it. The I1 is the intersection of these 3 prime ideals that we have here. And then we're done. Okay. Next time, we want to do the positive dimensional stuff. I think we've been spending a lot of time on primary decomposition, but it's a really good one. It's probably one of the most, I think it's one of the most useful of the computer algebra things to understand, because oftentimes when you just do the algorithm itself, it can just sit there and go into never land. But whereas, and if you don't know how it works, you're out of luck at that point. But if you have some idea, you can do this kind of stuff by hand, and sometimes you can find a faster way that it got stuck on something that it didn't really either need to do, or it was doing it in a bad order or something like that. So that is, so that one was that. But anyway, what you should do is take a look at, here, let me show you another example now, okay? So all of those, I mean, so we actually solved that one. I was thinking it was going to be a little more than that, but oh well. Here's a positive dimensional ideal. We'll do it over the rationals. This is in the same file. It looks very similar. It has a bunch of things. It's coming from a different graph, which I'll explain. Oops, I didn't mean to do minimal primes, but I did. And now I want to, how many, let's do OO/dimension. Okay, what are the dimensions of all the minimal primes? Now there's things that are of dimension 1. How are we ever going to handle things of dimension 1? This is all dimension 0 stuff. And there's a trick that we're going to do. And well, we can talk about it. But and here are all these things. Notice that there's lots of these things. 3 of dimension 1. Now I'm going to do, that was O49. I'm going to O49. And I'm going to look at what the degree of each one is. So the 3 things of dimension 1 are degrees 2, 2, and 6, whatever. That's just that's a degree of you know, as a variety somehow. But these are all the points now, and some of these. But what's going to happen in this case is if I do the primary decomposition, no, if I do I is equal to the radical, this one is not equal to its radical. So this one has primary components in it. So we'll have to figure out how to do it. Any questions on this? Is this too fast? Is this something that you should definitely take this and play with this file? I tried adding these functions at the beginning to get you going. Where are these functions? My factors is you can read about too, but univariate is the main one. What it does, this is taking the list of all the variables except for v, because that's what you have to give to the eliminate command to eliminate those variables. So this makes the list of all the other variables other than v. The way you try this is you actually try it. You take this line, copy it, and just try it on yours. And then this eliminates it. This gives you an ideal. And if num_gens is not equal to 1, then it's not that my logic is wrong. It just means that I was not 0-dimensional. So I should have said I is not 0-dimensional. And so it takes the very first generator. My factors is this function up higher that takes the factorization of it and gives you the thing so you can just work on it with it directly. You might not like that. You might like to see it. So you might just want to do factor of j_0 and just see the things in hand. But yep.
How did you load all of those functions at the beginning?
So here's the way the file has this is week9.m2. There's this line end minus minus. Macaulay 2, when it sees the word end at the beginning of line, it stops reading after that. So because I mean, there is no other place that you'll start with the word end unless you want to make a function called end, in which case you're kind of screwed because it will stop reading at that point. But at any rate, and then I restart, and then I have to be in that directory. I have to be in the same folder, and then I can do this. Or I could set the path and then load this, or I could load the entire the full path of this whole thing.
So whatever we called it, that's what we would put in the load.
Yes. And then these are just some functions. The reason these other functions exist is that if I have maybe I should explain to you the other trick that we need. And but it's for maximal independent sets, and I think it's going to be too late to do that. So maybe we do it on an example, and if it is not understandable, you tell me, and we won't do that now. So we're going to go back to our example, which is exercise B, problem B, right here, okay? And we're going to do it over Q. It's a polynomial ring in x1 to y4. Okay, and what I want to do is I want to get rid of those dimension 1 components, or I want to work on those dimension 1 components. And we already did these things, and actually we also, so here, yeah, see if I do this, let's just do the components. And if I do dimension of each one, it's 1, 1, 1, and a whole bunch of zeros. If I do degree, I get 2, 2, 6, and a whole bunch of small numbers. Radical and degree, notice what happens here. The degrees, each of these components correspond to the same one. These 2 3s, though, became 1s. That means these are primary components corresponding to those primes. Everything else looks like it didn't change, so those are all primes probably. 7 is 0, 1, 2, 3, 4, 5, 6, 7, which is this guy. So we can take a look at that, and this is what that ideal looks like. So is that primary? Well, we can look at its radical, and sure enough, it's a prime ideal and it's a maximal ideal. It's all 8 variables appear here. So in fact, that means it is primary. Right, because any other component would have to be embedded on that. Because when you radical, you could have other things, but they're all going to be larger primes, and there can't be any larger primes. So in this case, this is a prime ideal, and the other one is a primary ideal. It's kind of a big mess. So it's very hard to tell what's going on here. You have x. Notice that this factors x4 times x4. I mean, this looks like it should split into 2 things. But one of the factors is y4, and the other is x4 plus 1. But this is x4 plus 1 quantity squared. So splitting by this doesn't help out a whole lot. So so this is where you stop with primary stuff. Okay, now what we can do, so the dimension was 1, degree is 10. And now it says here, exercise is to, oops, shoot, where did I put it? I put it in the wrong place. So this is the independent set stuff, okay? So remember so in the homework, we had you could get the independent set. So the way this works is it takes the initial ideal of I in whatever order you're in, and then gives you what those independent sets are. But it's very confusing output. It's actually very bad output. This y1 comma y4 makes it seem like y1 comma y4 is an independent set, but it's not. Usually you get a set of monomials, square-free monomials. It would be y1 times y3 times something. And it's all, the independent set is the support of the first one. This makes sense, actually. So maybe at the board, should say what's happening. Yeah, I'm gonna stop sharing for just a bit, so that you can see my see the thing better.
You're going to say how these.
Yes, actually, maybe that's a good thing to do now, because otherwise, trying to do all of this stuff at the end here is I'd rather do it so you can actually understand it for next time. So let's actually talk about where these ideals come from. Are there any questions on the actual code or stuff like that? So what's worthwhile is to, like that univariate scope. If you're doing that all by hand more than once or twice, write a function for it, and then keep a file with your function. In reality, there should be tests in that. In reality, it should be a package also. So I might show you next time how to do that kind of stuff in Macaulay too, because it's extremely valuable to be able to do. And but for now, let's figure out where these ideals came from. So these are Kuramoto ideals. And it comes about from dynamical systems, okay? So let's start there. So suppose I have a graph. Actually, I'm not sure which order this, I'm going to name them though. Actually, I'm going to start with 0 and 1, 2. We'll make a triangle here. And then 3 and 4. This will unfortunately not quite mesh with the one, whichever one I use, because I can't remember what the order of these things is, but it's going to be similar. So the idea is you're going to have these things. It's a graph. You're going to have an oscillator at each one. So you're going to have theta sub 0 of t to theta sub 4 of t are oscillators. Think of them as like fireflies. Okay, they're all just going like this, you know, and everything's cool. There's actually a great video. How many of you were in Hal Shank's lecture on this stuff? Okay, so this is what this is all coming from. Okay, but nonetheless, okay, so you have this, and what we're going to have are differential equations for each one of these things. Each oscillator is going to depend on its neighbors. So theta I dot, so the derivative of this guy, is going to equal something. And that something in the Kuramoto model, it's a simplified model, but and this is the homogeneous Kuramoto model, which is even simpler. It's going to be the sum of all j in the neighbors of I. Okay, so you have a graph G that you start with, and you get this sum of the neighbors, and what do you get? You get sine of theta j minus theta I. Okay, that's it. That's the set of differential equations, and so you would like to understand the set of differential equations. Now it turns out this is a what's called a gradient system, so there's no chaos or any of that kind of stuff. So the question is what is the long-term behavior? So like, for instance, if I have 5 guys here and they're all flashing their lights at each other, and they're somehow staying in one place, or which wouldn't happen, that would be a more complicated situation. Do they all start flashing in sync? And so that's a question, and it will depend on the neighbors and so on. If you have a lot of these things, it turns out that they do, which is kind of cool. But now what that means is, how do you tell long-term behavior of something like this? You take the right-hand sides and set them all to be 0. Okay. So I'm going to set the right-hand sides equal to 0. That's 5 equations, because we have 5 of these guys. Now, if you think about it, though, there's a few things. If I shift all the thetas by the same thing, like if I change all these to be theta j to be theta 0, theta j minus theta 0, then the differences never change, and I can essentially get rid of one of the variables. Okay, so I'm going to say, without loss of generality, we can assume that theta 0 of t is equal to 0 for all t. So we just shift it, and then we have all these things. So that's a change of coordinates from the thetas. So we'll just assume that. And then the second thing is that we're going to make this algebraic. And how do we make it algebraic? What we do is we let xi be cosine of theta I, and yi equals sine of theta I. And then what do we have? We have that sine of theta j minus theta I. What does this turn into? It depends if you've been teaching calculus lately. So what is it? It's sine theta j times cosine theta I. Well, actually, because of the minus, it's plus. No, it's minus sine of theta j. But here's what it really is. What's kind of interesting. This is, let's see if I get this right. I have it's either plus or minus of that. Actually, I'm not sure which. Okay. But it's kind of interesting. This sine term turns into a 2x2 minor, which in algebraic land is always a good thing. Okay, this is a nice rank 4 quadric, xi yj minus xj yi. Just very nice. Okay, but that's only one of these terms. But if you translate this, then what do you get? Well, notice that the theta I is not changing here. Only the theta j is changing. So I'm going to call that f sub j. For the j, f sub I. And this is going to be the polynomial, which is the 2x2 minor of xi, xj, and then the sum of yi for I in, sum of yj for j in the neighbors of I, and the sum of xj for j in the neighbors of I. Right, that's, if I take this thing and I add it to the next one, that is just going to be adding it's a linear function on one of the columns. So I'm just adding up for every, I screwed up. I want this to be XIYI and XJYJ, but I don't, but only it could be either way. Doesn't really matter. Now I might have screwed up the sign. I'm not sure. Okay, good. Yeah, I think that's probably still okay.
So it's fine if no name is fine.
Yeah.
That's what I'm saying.
Okay, but in any case, so the xi here is not xj here. This is yi. Okay, so these are all staying fixed. That's this. No wonder if you were confused before. You had plenty of reason to be confused because I wrote down exactly what I didn't mean. And now you have, and this is also wrong. Because I changed that around. This has to change to xj, and this is yj. Okay. And now what are we doing? Our equations, so the ideal that we want is f, there's one more change I want to make, but let's not do that yet. I have f0, f1, up to f, how many ever we have, f4 in this case, okay? So whatever, how many vertices of G we have, that's how many of these things we have. By the way, notice that if I add up all of these things, what do I get? I'm going to have a sine theta j minus theta I here, but in the jth one, I'm going to have the opposite way. They're going to cancel. So in fact, the sum of all these polynomials is 0. Okay, but now this is the algebraic thing, but we really want that it comes from sines and cosines. So we also want to add x0 squared plus y0 squared minus 1 x4 squared plus y4 squared minus 1. This would be our one of our ideals. So there's several different ideals of interest here. So let me write them down. So given a graph G on vertices, say 0, 1 up to n minus 1, okay, we get several ideals. So the first ideal is, let's call it I sub G. This is going to be just the F's, not for, don't put the other ones in, okay? So this is going to be generated by F1, F0 up to Fn minus 1, where F sub I is equal to the 2x2 minor xi yi sum of xj for j in the neighbors of, I've used 3 different notations for neighbors here. I should have been a little better about that. Of I in j, and the same here. And this is y sub j. Okay. So this is an ideal in two n variables. And that's homogeneous, and it's generated by 2 by 2 minors of some nice matrices. So there's the question here. What are the primary decompositions of the IGs? This is an open question, okay? Completely open. You'd think that, in fact, it should have some really nice answer with the combinatorics, but I'm not, Hal and I don't know. Actually, we did this stuff also with Heather Harrington, who's now running one of the Max Planck Institutes in Dresden. Okay, so in any case, what are the primary decompositions? What's the dimension of it? Good question. Okay, so is it ever prime? I mean, there's all sorts of questions. When is it radical? It actually, so far on lots of examples, this appears to always be radical, but I don't know if it is or not. Anyway, that's one ideal. Here's another ideal. Is I'll call it JG, but we don't actually call it that in the paper. This is going to be given by F0, but now I'm going to give, since I can make the first oscillator be 0, that means that x0 is 1 and y0 is 0. So I'm going to set x0 to be 1 and y0 to be 0 on all of the polynomials. And then I'm going to add in all of the other ones, x1 squared plus y1 squared minus 1, dot, 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 up to xn minus 1 squared plus yn minus 1 squared minus 1. Notice that there's two less variables now. There's 2n minus 2 variables. And this is the ideal that I gave you two different graphs here. One of them was the zero-dimensional one we just did. I'm pretty sure that one was a square. Actually, I'm not sure which one was which. So we'd have to take a look. In fact, maybe we should take a look at which one it is. But in fact, we have 2 minutes left. We're not going to do that. But this is a set of ideals that I think is very interesting. This one especially should really be attackable combinatorially, but I don't know how to do it or algebraically. Anyway, it's something I'm very interested in. So if you're if it's something you're interested in, it looks like just some ideals, but the number of papers written on Kuramoto ideals coming from an algebra combinatorics thing, you just wouldn't understand how staggering the number of the sizes of the communities there are. Why are they interesting? That's a good question. I think that it's because that's an excellent question. It's because there's a lot of behavior that seems to be well modeled by this kind of thing. It might be, you might generalize it a bit more. You might so you want oscillation. This is the first simplest oscillation you could have. You could add in sine of 3 times something terms or sine cubed terms, or you could add in cosine terms. That's actually makes it really awful. But you can do things like that.
I mean, this is all coupled oscillator stuff, and there's a lot of like one-dimensional heat transport, which is really important for like electronics and stuff that's modeled by like a Fermi-Class Coulomb chain, stuff like that, which this all encapsulates. So this is like massive for physics and stuff.
So, okay, so written in terms of the trig functions, it's a nonlinear equation. When you algebraicize it, does it become linear or?
No, not at all. There's no way it can become linear. So, but
So it's trackable. Example of
so there are theorems that are the following sort. So you can look at all the solutions. We found the solutions. There was a one-dimensional, well, there were a bunch of zero-dimensional things. And in the second example, there's going to be a one-dimensional family of examples and a bunch of point examples. Those things, if you look at all those solutions, you can figure out which ones are stable by looking at the Jacobian of the corresponding system and just seeing if it's negative definite or not. And if it's negative definite, only at the point where all the cosines are 1 and all the sines are 0. That's the angle zeros. That means they're all in sync. You've subtracted them, so they're all doing the same thing completely in sync. And so there's a theorem that says that if you have enough edges in your graph, then it always, the only solution to that is the self-sinking solution. And then the question is, what happens when there are less edges? And then there's the result also is that below a certain critical threshold, which is essentially 3/4, any graph that has that degree essentially will, you don't know, it might or might not, but there is a graph that will not be self-sinking. We'll have a weird other solutions. The other solutions are very weird and really cool. And what Hal and I and Heather tried to do is we tried to take all these small size graphs and figure out which ones can you tell from the graph whether it's self-sinking or not. And we found some that are not self-sinking. And this is what Hal did in his talk. Basically, the pentagon is the first example. Well, the square is sort of an example, but that has nonlinear behavior. But the pentagon is the one, the hexagon is one, and as is the pentagon with a triangle sticking off of it. And then you go up to the next higher size, and you find a bunch of things of size 7 that are that all have a pentagon. You can just see it. There's no other chords across the pentagon, and so you have a really great conjecture. But then you get to 8. And then there's the diamond inside of a diamond, like a square inside of a square. And that one does not have a pentagon. And it also has a so-called exotic solution, which is not that exotic always, but yeah.
Do you guys have good methods for finding these stable solutions? So for example, like if you've got like an excitable medium, you just have a solution that's going around in a circle, right? When you're talking about these cycles. Right, that's a
yeah, that's right. So the answer is that the algebraic techniques only work in small number of variables because it's hard. The algebraic complexity gets quite large. What is good about these things, though, is that the dynamical systems people have ways of finding stable solutions really fast, but they don't know they have them all. And this process gives you an entire list of solutions, and that you can actually check each one and see. And it has found ones that they did not know existed because they're in such a small region that unless you start in that region, you'll never see it. So I think the advantage of this stuff is it gives you more structure about the systems. And I think that the primary decompositions of these, if one could understand it, would do that too. Now, do the dynamical systems people care about this? They're slightly interested, but they're not. But they really prefer things with huge numbers of huge graph size. But on the other hand, I did some stuff with Steve Strogatz and Alex Townsend, and it used some of the stuff we did here on small graph sizes to that with some constructions allowed you to figure out behavior that happens much higher size. So doing these small size things can actually help, but it gets very hard. I mean, I'm showing you this graph has 5 vertices or 4 vertices or something like that, 5 vertices, I guess, and up to 8, you can start using numerical algebraic geometry methods in Macaulay 2 to solve it. But then you can maybe go up to 9 or 10 vertices, but the primary decomposition is out of reach at that size. So the question is could one find a way of doing that? That would be kind of cool. So, or even finding the points, because actually none of the stable points can occur on higher dimensional components. But it's weird. This ideal here, the one I showed you that was not reduced, it has those primary components on it. This ideal, nonetheless, if you don't put these xi squared, this thing is reduced, and it's a radical ideal. And but when you throw this in, it just screws it all up. So it's very mysterious. But anyway, it's an interesting kind of behavior. And we've gone over. So, and it's 3 hours, and over 3 hours is a lot. So sorry about that. So next time I think I do want to still spend a little time doing the positive dimensional stuff. And then we'll really, you will have then the techniques to take any ideal in your research. And if Macaulay 2 or whatever system can't handle the decomposition of it, you might have a chance of figuring it out. That's a big thing in a lot of these areas, especially, I mean, Alan Knudsen is always trying to find the decomposition of ideals and stuff like that. And so it's actually, it's a valuable skill, I think. Okay, that's all for now.